Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. In this video, I'm working through question 31 of the Blacktown Boys High School 2020 Year 12 Math Advanced trial. I was working through this question with a student who I teach face-to-face, and we ended up running out of time before we could get through all of it. So I thought, rather than leave them hanging, I'd finish working through the question in this video, and that way they can take a look in their own time and see how it all works. So the question tells us that a particle moves in a straight line. At time t seconds, its displacement is x meters from the origin O on the line. And the velocity of the particle is given by v is equal to 2 minus 4 cos 2t for a domain of t between 0 and 2 pi inclusive. So it's a classic setup for applications of calculus. We're going to probably see some differentiation, a bit of integration, and then because we've got cos 2t as part of our velocity formula, we'll see the periodicity of the cos curve and how that plays out. So we've got 5 parts to the question. Part A asks us to find the initial velocity of the particle. Part B wants us to find all the times when the particle is at rest. Part C asks us to sketch the graph of v as a function of t. Part D asks us to find the acceleration of the particle when t is equal to pi on 2. And then part E says to find the exact displacement of this particle when t is equal to pi, given that its initial displacement is 3 meters to the right of the origin. Alright, so for part A, we want to find the initial velocity, and whenever you see the word initial in these kinds of questions, what we're dealing with is t is equal to 0, in other words at the start of the time period. So I'll just write out our velocity formula. We were given v is equal to 2 minus 4 cos 2t, and we had our domain of t between 0 and 2 pi. So if we just set 0, t is equal to 0, we'll get v is equal to 2 minus 4 times cos of 2 times 0, which is just cos 0, which would be 2 minus 4 times 1, since the cos curve starts at 1, and then that's 2 minus 4 is negative 2. And then we have to remember our units, so displacement was in meters and time was in seconds. So 2 meters minus 2 meters per second is the initial velocity. Boom! Alright, so that's part 1, or part A. So part B wants us to find when the particle is at rest. And in this case, the words at rest, what they equate to is v being equal to 0. And you can kind of see how this question is guiding us towards sketching the chart, because we're looking at our vertical axis intercept, and now we're looking at our horizontal axis intercepts, and that'll help us when getting to part C, which wanted us to sketch the curve. So if we want to set v equals 0, we just take our same formula and we have the v being 0 now, and we're going to solve for t. So 2 minus 4 cos 2t. So we'll just do some rearranging. I'll bring the 4 cos 2t over. So 4 cos 2t is equal to 2. Cos 2t is equal to 2 on 4 or a half. And at this point, I'm not going to go any further yet. The temptation might be to take the inverse cos of both sides, divide by 2, and get your first value of t. But I actually think that leaving this in terms of 2t and kind of graphing cos 2t, or just cos of x where x happens to be 2t, I think we can find all of those solutions and then as a final step divide them all by 2 to get t by itself. I think that's going to be a bit easier to grapple with. So what we'll do is I might just draw up a little axis here. And actually what I should note is our domain was t between 0 and 2 pi, but if we're thinking about 2t, then I need to double all of this domain to get 2t in the middle. So we'll have 2 times 0 is 0, 2 times t is 2t, and then 2 times 2 pi would be 4 pi. So actually I want to chart this up between 0 and 4 pi to get the full cycles that we're going to deal with. So coming across here, we'll have, say, pi, 2 pi, 3 pi, and 4 pi. So that's probably all we have to go across. So let's just label. So we'll have here 2t is our axis, because I'm just plotting a normal cos curve with 2t as our, it's almost like a substitution that we're doing, but just on the chart. And I'll just call this y. We're plotting y is equal to cos 2t. This will be 0. I'll call this 1, and I'll call this -1. So we're doing a sketch of just cos 2t in the lead up to part C, where we're going to sketch this curve proper. So we'll have pi, 2 pi, 3 pi, and 4 pi. And hopefully you're familiar with the typical cos curve, which will start up at 1 and will come down and hit its low point at pi, back up, hit its peak again at 2 pi, and then here we're going to repeat because we've got the wider domain. So we carry on, so hitting -1 at 3 pi and then getting back to the top again at 4 pi. So that's our y is equal to cos 2t curve. And it's probably worth annotating on here that, just really highlighting that the periodicity here, getting from peak to peak or trough to trough, or from any point to any equivalent point, is 2 pi. It's going to be handy for us to keep that in mind. Now, remembering we're concerned with this curve being equal to a half, so if this is a half here, this is -1/2, if I just draw a dashed line through here, because that's what we're concerned with, what we see is that there are 1, 2, 3, 4 points in this domain where we have this intercept. So the first mistake you can make that you need to be careful of is to forget to update your domain to be in terms of 2t and only end up with the first 2 solutions rather than all 4. So that's an important thing to keep in mind. From here though, I think the key to getting all of these points is to get the first point and then understand the relationship between that first point and the other 3 points. So we're going to have 2t being equal to, there'll be 1, 2, 3, 4. So there's going to be 4 solutions. And now we'll just do the work to kind of work those all out. Once we find them, we'll just divide them by 2 to get t by itself. Now the first solution, we can just use our calculator. When does cos of 2t equal a half? I can just get the inverse cos of a half. 60 degrees, if I do 60 on 180, that's pi on 3. So that's our first solution, pi on 3. So if I just annotate, these are the 4 points that we care about. And we know the first one happens at pi on 3. Okay, now the second one I might just leave for now, because using this periodicity of 2 pi, getting from this first part of the curve, going a full cycle, and then getting to the equivalent part of the curve in the second cycle, we know that that distance there, the distance from here to here, must also be 2 pi. So my third solution here will just be the first solution plus 2 pi. So if I, maybe just over to the side, if I just, maybe I'll use this section over here just for rough working. What we'll get is pi on 3 plus 2 pi is equal to pi on 3 plus 6 pi on 3. And that gives us 1 plus 6 is 7 pi on 3. So I know my third solution will be 7 pi on 3. And that's this point here, 7 pi on 3. Okay, now maybe I'll use a new color here. This second point, we haven't gone a full cycle yet, so we can't just add 2 pi, and we can't just add 1 pi. That might be tempting, but we know it's kind of more than 1 pi's worth. So how do we work out where this point is? Well, again, the periodicity does help us because we see starting at this peak, we've moved pi on 3 in this direction. And because the cos curve is symmetrical, what it means is that this point here will be the same distance backwards from the peak. So from this peak here, we've moved the same distance, in other words, pi on 3. So this second solution will actually be, we can say it's the 2 pi, we've gone 2 pi, minus this distance, which is pi on 3. So that's going to be equal to 6 pi on 3 minus pi on 3. And 6 minus 1 is 5, so that's 5 pi on 3. So this second solution is 5 pi on 3. And I'll just note that on the curve. So this is 5 pi on 3. And now, once again, we can use for the final solution the fact that we're going a full cycle. So we're just going another 2 pi from this point now. So our last point, our last solution will be 5 pi on 3 plus 2 pi, which will be 5 pi on 3 plus 6 pi on 3. And 5 plus 6 is 11 pi on 3. So this will be 11 pi on 3. So hopefully you followed that. I mean, you just need to be very careful about, I guess, the points that you're dealing with. And as long as you understand the cos curve, the basic makeup of the cos curve, I think drawing it will always be helpful to help you not make mistakes and see what you're dealing with. You can kind of get there. You use your calculator to work out the first point, and then you use your knowledge of the periodicity and the symmetrical nature of the curve to work out the other points. So that's 2t, but remember we want t, we want the values of t by itself, and I might just have to turn over just to get a bit more space, but turning over, what that means, if I just say we've got 2t is equal to pi on 3, 5 pi on 3, 7 pi on 3, 11 pi on 3. Then all that means is that t by itself will be pi on 6, 5 pi on 6, 7 pi on 6, and 11 pi on 6. And that's the answer to part B. So now we've got our, essentially what will be our horizontal axis intercepts. And in part A, we had our vertical axis intercept. So now for part C, we're kind of ready to sketch V as a function of t, which is what that question, what part C was asking us to do. So remembering V is equal to 2 minus 4 cos 2t for t between 0 and 2 pi. And now we're back to thinking of t by itself, so this domain is still the domain. We don't need to manipulate it now. yeah, let's just draw up an axis and work with what we know. So I might make this a big axis so that we can see all the features. So maybe I'll just go 2, 4, 6, 2, 4, 6. And because we're dealing with pi on 6, we know we're going to have to kind of have points that intercept this axis in kind of multiples of something on 6, 5 pi on 6. I might just get between 0 and 2 pi by moving up in pi on 6. So we'll go pi on 6, 2 pi on 6, 3 pi on 6, 4 pi on 6, 5 pi on 6, 6 pi on 6, 7, 8, 9, 10, 11, and then 12 pi on 6 gets us to 2 pi. So that's kind of as far as we need to go. So this is t, vertical axis is v, this will be 0. And because we've got 2 minus 4, we're kind of, we're not just going to be between 1 and negative 1 now, it's going to be stretched. I think if we go 2, 4, 6, negative 2, negative 4, negative 6, that should be enough to cover the amplitude of what we're going to see. So we'll have 1 pi on 6, 2 pi on 6, which would be pi on 3, 3 pi on 6, which would be pi on 2, 4 pi on 6, which would be 2 pi on 3, 5 pi on 6, and then 6 pi on 6 is pi, 7 pi on 6, 8 pi on 6, which would be 4 pi on 3, 9 pi on 6, which would be 3 pi on 2, 10 pi on 6, which would be 5 pi on 3, 11 pi on 6, and then 12 pi on 6, or 2 pi. So there are all the various points of interest, I guess. And I think the first thing we can do, well actually the first thing we can do is plot this vertical intercept, which we found in part A to be minus 2. So we know the curve is starting here at minus 2. We also have our intercepts of the horizontal axis, so at pi on 6, 5 pi on 6, 7 pi on 6, did I get, yep, 7 pi on 6, and then 11 pi on 6. They're our intercepts. It might also be helpful to just draw what is the midpoint, just very lightly, just as a reference point. What will be the middle of this curve, because it's not kind of centered at 0 anymore, it's been shifted up by 2. So the 2 out the front here is what shifts up the curve. The minus 4 inverts the curve so that we're starting from the bottom and going up instead of starting from the top and coming down. And then the 4 simply makes the amplitude higher. And the 2t here just means we have more intercepts, which we kind of did the hard work to work out in part B. So I can kind of know now that I'm going to get my peaks and troughs at pi on 2 will be the peak here, the trough will be at pi, and then we'll get our next peak at 3 pi on 2. I may have made a mistake here. So we got 6 pi on 6, 7 pi on 6, 8 pi on 6, 9 pi on 6 would be 3 pi on 2, not 3 pi on 3. So that's our next peak. And then we get to our final trough at 2 pi. And with those kind of points marked, we can now just kind of fill in the curve. And I'll do my best to not butcher this, but the key features are the intercepts. So we're just going to make sure we go through those. And then coming back down. And it's probably not the best drawing in the world, but that's the basic shape. I've kind of, a computer would do a much better job of drawing this, but this is the curve V is equal to 2 minus 4 cos 2t in this domain. Boom! I think the key point of this is noting these intercepts, like making the link between part A and B and here, part C, and then kind of just understanding the nature of the curve. We've still got our periodicity. We've flipped the direction of the movement, and we've shifted it and kind of stretched it vertically and then squished it horizontally. That's what all of these things do to the curve, and this too. So hopefully you followed along with that. Let's move on now to part D. So I might turn over just to get some space. So part D wants us to find the acceleration when t is equal to pi on 2. So the first thing you need to appreciate is, with these applications of calculus, the acceleration is the derivative of the velocity with respect to t. So what we need to do is differentiate this curve. So if I just note over here, v is equal to 2 minus 4 cos 2t, we want to differentiate this. So I think the key is to know that in general, the derivative with respect to x of cos x would be negative sine x. That's the key result we need to know. So if we want to differentiate this, the derivative, we can differentiate each part. The derivative of 2 will disappear, and we'd have negative 4 times the derivative of cos 2t. So we're kind of using the chain rule here. So we'd have times minus sine of 2t times the derivative of what's inside with respect to t, which would be just 2. So if I clean this up, the negatives will cancel, and 2 times 4 is 8. So we'll just end up with 8 sine 2t as our derivative. And that's the hard work done, really, because now we just plug in pi on 2. So when t is equal to pi on 2, our acceleration is equal to 8 times sine 2 times pi on 2, we'll just leave pi. And if you want, you can just plug that into your calculator. So pi is 180, sine of 180 is 0. So actually 8 times 0 will just be 0. And we need to remember our units. So we're moving in meters, and this is per second squared for acceleration. Boom! All right, now interestingly, and I don't know whether this would get all the marks, but if you look at the diagram that we just drew at pi on 2, we see it's a stationary point for the curve of v. So seeing that the acceleration is 0 is very consistent with that, because we know the derivative would be 0 at the stationary point. And maybe if you wanted to save yourself a bit of time and effort, you could have said, from the chart we can see that at pi on 2 it's a stationary point, therefore acceleration must be 0. I think maybe it's a bit more, maybe you get more comfort from just working through the mechanics and then using the chart to confirm that you haven't made a mistake. I think either way you'll probably get your marks. So that's part D done. So now we're going to move on to the final part, part E, and that wants us to find the exact displacement, and I'll just note that exact displacement when t is equal to pi. And we are given a bit of information here. We're told that when t is equal to 0, the initial displacement, x is equal to 3 in terms of moving in the positive direction from the origin. So that's going to help us, I think, as we work through what ultimately will be an integration because we're going to need to find our constant, and this will help us do that. So here we want displacement, which is x. And so what we need to know is, in terms of applications of calculus, the velocity is equal to the derivative of the displacement with respect to time. So now if we want to isolate x, we have to integrate both sides. So we get x is equal to the integral of v with respect to t. And so that means we're going to integrate 2 minus 4 cos 2t dt. And again, you can integrate each part separately. So the integral of 2 dt would just be 2t. And then minus 4 times the integral of cos 2t. And maybe over to the side, we can do a bit of side working here, because we know in general that the integral of cos x dx is equal to sine x plus c, but that's the key here, sine x. So if I want the integral of cos 2x dx, maybe what I can do is do a u substitution. So let u equal 2x. So du dx would be equal to 2. Therefore, dx would be equal to du on 2. So therefore, the integral of cos 2x dx would be the integral of cos u dx is du on 2, which would equal, I'll bring out the half, so a half times the integral of cos, which we know is sine. So sine u, again plus c, but I'll do all the plus c's over here. So substituting back in, we'll get u was 2x, so sine of 2x. So the integral of cos x dx was simply a half sine 2x. Now that might be a result that you've committed to memory, but I think using u substitution and working through the mechanics is always a good idea, just to make sure your memory hasn't failed you. So now what we can do is put that in. So it'll be minus 4 times a half sine 2t. Here we're dealing with t. And now I'll just do plus some constant, which captures all of the constants together that we would have encountered here. So I'll just simplify this a bit more. So that's 2t. 4 divided by 2 is 2, so minus 2 sine 2t plus c. And now we need to find this constant so that we can then just plug in t is equal to pi and get our exact displacement. So I might turn over for that. Remembering that when t is equal to 0, x is equal to 3, therefore we can say that 3 is equal to 2 times t, which is 0, minus 2 times sine 0 plus c. Now 2 times 0 is 0. As we saw before, if I take the sine of 0, I also get 0. So these two disappear and we just get c by itself. So therefore c is equal to 3. And now we can kind of finish off our curve, because we can say therefore x is equal to 2t minus 2 sine 2t plus 3 being our constant. Alright, so now what we can do is say when t is equal to pi, which is what we were concerned with, x is equal to 2 pi minus 2 sine 2 pi plus 3. Now, in terms of sine 2 pi, that's sine 360. Oops. sine 360. 0 again, so that drops out. And we end up with x being 2 pi plus 3. We've got to remember our units, so displacement is in meters. And I won't throw in a value for pi here because the question wanted us to find the exact displacement. So we can just leave it at that. That's the exact displacement. So, yeah, that's it. That's all 5 parts of that question. I think, I mean, at the end of the day, just classic applications of calculus. We've kind of covered the whole suite of things you might ever have to encounter in terms of both differentiating and integrating. Having the cos in there meant we had to kind of be comfortable with our trigonometry and our periodicity of the cos curve. But I think as long as you're methodical and careful, you can kind of get all the marks on offer for this question. So hopefully you did find that helpful. If that was helpful for you, please feel free to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please subscribe to my channel so that you can stay in the loop. All right, tick boom.